Welcome to Maths with EJD. In this video, we'll be talking about convolution theorem for Laplace transforms. If you remember, earlier on, we had talked about convolution theorem for inverse Laplace transforms. So here we're talking about the proper convolution theorem, which is not as, which will not take us all the way to inverse Laplace transform. All right, because the necessity for inverse Laplace transform lies in the fact that after taking the Laplace transform, we now need to take whatever we have got in the Laplace domain back to the time domain. But I mean, at the end of the day, I may also end up, after doing everything I need to do, I may just take one example to just refresh our mind on the idea of inverse Laplace for convolution. But the focus here is not about the inverse, it's about the Laplace transform itself. So the convolution theorem for Laplace transforms states that the Laplace transform of two functions the Laplace transform of the convolution, the Laplace transform of the convolution of two functions is the product of their individual Laplace transforms. So in short, if you want to take the Laplace of a product of two functions, then you just find the Laplace of each function and multiply them together. Basically, that's what this is talking about. So this is a powerful property. This is a powerful property that simplifies this is a powerful property that simplifies the process of finding the Laplace transform of certain integrals involving products of functions. Okay, so let's look at the statement more officially. Statement of the convolution theorem. So more in a mathematical sense now. So if f of t and g of t are two functions whose Laplace transform exists, whose Laplace transforms exist, then the Laplace transform of their convolution is the product of their individual Laplace transforms. Easy peasy. Specifically, if you take the Laplace of the convolution of f and g of t, it is simply the Laplace of f of t multiplied by the Laplace of g of t. That's what the rule simply says, where the convolution, this is the law now, where the theorem where the convolution f star g of t is defined as f star g of t, f convoluted with g of t equals integral from 0 to t of f of tau g of t minus tau d tau. So we used this previously to get the inverse of convolution. So at the end of everything, I'm just going to refresh memory on this again. So this is another very important one. Okay. So let's look at an example or two. So example, find the Laplace transform of the convolution of f of t equals e raised power 2t and g of t equals sine t. Okay, here we have step one. Step one is to compute the Laplace transforms of f of t and g of t. So first of all, we know that the Laplace transform of f of t, which is the same thing as the Laplace of f of t, is e raised power 2t, right? So we have e raised power 2t, okay? And that is simply the same thing as 1 over s minus a. I mean, 1 over s minus 2, since the Laplace of e raised power at is 1 over s plus a. So this should be, I mean, Laplace of e raised power at is equal to 1 over s minus a, yeah? So that's the Laplace of e raised power 2t, 1 over s minus 2. On the other hand, right, we also have the Laplace of g of t, which is the Laplace of g of t sine t, okay? So I remember I used the exponential, the Euler identity or something to find, so joint result for sine and cos in this situation. So the Laplace of sine t is actually 1 over, so you know that should be 1 over, it should be a over s squared plus a squared, right? So now our a here is 1 because the coefficient of t here is just 1. So we have 1 over s squared plus 1. Okay? 1 over s squared plus 1. So for cosine, it will be I think s over s squared plus a squared also in that situation. So with this now, we can do the convolution thing. We go for step 2. So in step 2, we apply the convolution theorem. Apply the convolution theorem. So using the convolution theorem, the Laplace transform of the convolution is the product of the Laplace transforms. So applying the convolution theorem, we have the Laplace of the convolution of f star g of t, k, and that is the Laplace of f of t multiplied by the Laplace of g of t. Okay, so that gives us the first case 1 over s minus 2. The second one is 1 over s squared plus 1. So we have 1 over s minus 2 multiplied by 1 over s squared plus 1. And that is what we get. That's 1 over s minus 2 into s squared plus 1, basically. Okay. We can then conclude that thus the Laplace transform of the convolution of f of t equals e raised by 2t and g of t equals sine t is Laplace of g star Laplace of f convoluted with g of t is simply 1 over s minus 2 into s squared plus 1, like that. Okay, this shows how the convolution theorem simplifies the calculation of Laplace transforms for complex integrals, turning a potential difficult problem into one of simply multiplying two transforms. Okay, now, just like I said the other time, although this is totally not necessary, but I mean, it's, you can imagine it as a refresher course in Laplace transform. So let me do this and then go back to this. So can we just take a kind of revisit? A revisit to convolution theorem, convolution. So once we get these two and we put them together, we are good, right? But then I want to take it a bit further just to remind us of what we did with convolution using two different approaches. So a revisit to convolution theorem, okay, for inverse Laplace transform, inverse Laplace transform. So I'll just do that in form of an example since the main issue has been done in the past, okay? So the question here is, okay, we have this, find the Laplace transform and the Laplace, so let me call that example, right? Find the Laplace transform of the convolution of f of t equals t and g of t equals e raised to minus t. Okay. Then find the inverse Laplace. Then find the inverse Laplace transform. Okay. And find the inverse Laplace transform. Okay. So how do we take care of that? So solution now. So we have f of t to be t, and we have g of t to be e raised to minus t. Okay. So automatically, since we are told to first of all find the Laplace transform, so we know that f convoluted with g of t is simply the same thing as t e raised to minus t. Okay, so the Laplace of f, or better still, I can just go straight. Laplace of e raised to minus t, as we know it, will just be the Laplace of t multiplied by the Laplace of e raised to minus t. Okay, and from that we know this is the same thing as the Laplace of t is just straightforward, that is 1 over s squared, and the Laplace of e raised to minus t is 1 over s plus 1 because of the minus t, that's plus 1. So in this case now, we just know that that convolution simply gives us 1 over s squared into s plus 1. So this is the Laplace of that convolution easily. So we can just conclude, therefore, the Laplace of f convoluted with g of t is simply 1 over s squared into s plus 1. So now here, we are told to find we now need to find the inverse Laplace of this particular expression now. Okay, so because it says then find the inverse. So we've taken the first step to find. So this is what we really need for Laplace transform. So we don't need to go further if all we are looking for is Laplace transform. But just to refresh our memory, that's why I'm going further now. So and I'll say to find the inverse the inverse Laplace the inverse Laplace transform of f convoluted with g of t. Okay, so we already have so it means we now need to do. So it's more like we are undoing what we did already, right? It's looking like we are looking for f convoluted with g again. So we can say this is inverse Laplace of the Laplace of f convoluted with g of t. So it's more like we are taking it back to where we came from. And that normally that should be t e raised by minus t. But in fact, what this is probably going to give us something even simpler than that t e raised by minus t. But that is analytically exactly the same expression as that thing. Okay. So that will be Laplace inverse of what we got there as 1 over s squared into s plus 1. So the Laplace inverse of 1 over s squared into s plus 1. So the result is going to be way easier than even t e raised by minus t. Of course, this just cancels out as we know. So we just have it back to f convoluted with g of t equals the Laplace inverse of 1 over s squared into s plus 1. So now looking at that expression, right, we discover that um we need we need to do partial decomposition. What's that thing called now? Partial fraction decomposition, exactly. So we need we need partial fraction, partial fraction. We can also take them apart and take it back to where we're coming from, but we can even make it easier, right? We need partial fraction decomposition for 1 over s squared into s plus 1. Okay. So, and to do that, what we just do is we have 1 over s squared into s plus 1. That is similar to a over s plus a over s, right? Because this s squared, s is repeated linear roots. So we have a over s plus b over s squared, then plus c over s plus 1. So if it had power 3, so would have had a over s plus b over s squared plus c over s cubed. Then s plus 1 is just linear and it's not repeated, so we just have s plus 1. So this way now we are looking for a, b, and c. Okay, so we can multiply through by the LCM, which is 1 equals a into a cancels 1s, so we have s into s plus 1. Then we have b, s squared cancels that, we have s plus 1. Then we have c into s plus 1 cancels s plus 1, so we have s squared. Okay, we have just s squared. So this is the expression we have now. Then we can use the cover-up method. I guess I want to switch over now. So let's go this here, and then I go green, right? So using the cover-up method, cover-up method, So cover-up method helps us to quickly get rid of whatever we don't want. So we can set s to be 0. Once you set s to be 0, anywhere there's s, it will go. So because s is 0 here, so this will go. S is 0 here, so b will remain. S is 0 here, so it will also go. So we just have so it means we have only okay, I mean, we already know A and C are gone, only B will remain. So we just have, on the left-hand side, we have only 1. So we have 1 is equal to, on the right, A is gone, B remains. So we have B into 0 plus 1. C S squared, S is 0, 0 squared is 0, so times C, that's gone. So we just have 1 equals B. So basically, B is equal to 1. Done. So the next thing, we have got B, so we need to get other things. So we also know that if we set S to be minus 1, anywhere there is S plus 1 will be gone. So if we set S to be minus 1, this will go and this will go. And then we can have C left, okay? So we set And how do we get what to set, right? Just say s plus 1 equals 0. And that means s is equal to minus 1. So, and once s is minus 1, it gives you what you want, okay? Like that, okay? So, next, set s to be minus 1. So on the right, we just have 1. Nothing, there's no s with that. Then on the left now, this will go, a will go, b will go. So we just have c into minus 1 squared. So c into minus 1 squared, that's s squared. So 1 is equal to c into 1. That's c simply equal to 1. So a is 1, I mean, B is 1, C is 1. So lastly, we don't have anything we can set directly, but we can always use any number we like. Okay. We have used 0, we have used 1. So we have used minus 1, so we can also use 1. Okay. Because once you exhaust everything, you can just use anything outside of that range. So we can now set S to be 1, since we have not used 1 already. So on the left, we have 1, and we have um, a into 1 into 1 plus 1. So that will be a into 1 into 1 plus 1 plus b into, so b is b into s plus 1. So that would be into 1 plus 1 and plus c into s squared. S squared, so s now is 1. So we have 1 squared. Okay. So we have 1 is equal to a into 1 into 2 plus b into 2 plus c into 1. So we tidy that up, we have 1 equals 2a plus 2b plus c. Interestingly, we already have b and c to be 1 each. So we have 1 equals 2a plus 2 into 1 plus 1. Okay. So that is 1 equals 2a plus 2, 2a plus 2 plus 1. So this is 1 minus 2 minus 1 equals 2a, right? Yep. So 1 cancels 1. So we just have minus 2 equals 2a. All right. That's 2a. That simply means that a is equal to, when we divide through by 2, a is equal to minus 1. Okay. So we have all our results. So we have, so a is minus 1, b is 1, and c is 1. Therefore, we go back to where we are coming from. We go back to this expression. Okay. So we say, therefore, 1 over s squared into s plus 1 is equal to minus 1 all over s plus 1 all over s squared plus 1 all over s plus 1. So we can now easily take the inverse Laplace of this expression, because that's where we are coming from. So we can say the inverse Laplace of 1 over s squared into s plus 1 now is equal to, so this is like the Laplace inverse of minus 1 over s plus the Laplace inverse of 1 over s squared plus the Laplace inverse of 1 over plus the Laplace inverse of 1 over s plus 1. Okay. So this is like, cos minus 1 can come out. So we have minus 1 Laplace inverse of 1 over s, or better still, just minus, because minus 1 is still that. Laplace inverse, right? Plus Laplace inverse of 1 over s squared plus Laplace inverse of 1 over s plus 1. Okay. So Laplace inverse of 1 over s is simply the same thing as, so this would be minus 1, right? You know, it is the Laplace of 1 that gives you 1 over s. So this would just be minus 1. And then the next one, L inverse over s squared. So for s squared, right, we have, so it is t. The Laplace of t gives us 1 over s squared. Then Laplace inverse of 1 over s plus 1. What gives us 1 over s plus 1 is just e raised power e raised power minus t. So this would be e raised power minus t. So we can rearrange this now anyhow we like. We can say this is t minus 1 plus e raised power minus t. Okay, so that is the Laplace inverse of 1 over s squared into s plus 1. Now, the interesting thing about this is that this is expected to be the same as that convoluted stuff, which is t e raised power minus t. So this would actually be t e raised power minus t. So how do you confirm that? Okay, you can evaluate t e raised power minus t. If you put 0, so this is 0 minus 1 e raised power 0. That's also 0. So that is 0. So if you put 0, that's 0 times e raised power this, and it's 0. If you put 1, so 1 minus 1 is gone. So you have e raised power minus 1. And this will also be e raised power minus 1. So they are basically the same. Okay? That's that original thing you're coming from. Now, if you don't do it this way, right? Another way is another approach. Let me switch over now. Let's go green here and then say this now. So um another way another way to find the inverse of the inverse of the inverse of 1 over s squared into s plus 1 is to use the convolution convolution theorem for inverse Laplace. That was exactly what we did for the convolution the other time. So that's like a second method, right? So, and that's where you say that the Laplace, so we know that okay, yeah, we remember that this expression now, that f convoluted with g of t, okay, is simply the same thing as integral from 0 to t of f of tau. We talked about that here, right? G of t minus tau d tau, okay? So we can use this directly to get the same results we just got here now, okay? This same results we got here now. We can use the same approach to get. So take note, t minus 1 plus e raised power minus t. That's the result. So if we do that here, so we can remind ourselves that f of t is t and g of t is e raised power minus t. If that is the case, then we have f convoluted with g of t is equal to integral from 0 to t of f of t, f of tau now. So since f of t is t, so we have this tau, f of tau now will be tau because f of t is t, so f of tau will just be tau. And then we have g of t minus tau, okay? If g of t is e raised power minus t, so g of t minus tau will just be e raised power minus t minus tau, okay? Minus t minus tau d tau, okay? So that's what we have there. And since we are integrating with respect to tau now, then we can proceed like this. We have integral from 0 to t. So tau is the variable we are working at. So tau dot e raised power minus t dot e raised power minus tau, okay? Is that what that should really be? No, e raised power tau, not minus tau. Yeah, this is e raised power tau, because if you expand this minus t plus tau, okay? So the tau, so we can keep only the taus alone and move out t. So this one will not be here now because our focus is on tau. So we have e raised power minus t out here, integral from 0 to t, then tau e raised power tau d tau. And so here we can use integration by parts. No, is it integration by parts? Yeah, integration by parts. Exactly. Yeah, we can use integration by parts. So again, this is f convoluted with g of t. So using integration by parts, using integration by parts. So what do we really mean? It means that we can, anything that will go off, we can make it u, and the rest can be dv, okay? And if that is the case, we can say that f convoluted with g in time is e raised power minus t there, integral. Now here, we are not going to have that. The integration by parts is simply something like this: integral of u dv is equal to uv, okay? Uv minus integral of v du. So our u is tau, right? So it means we have this now. Okay, we can box this. So we have this integral of e raised power minus t into, not integral now. So u is tau already. Then v, you have e raised power tau. So if you to get v from that, you have to integrate. If you integrate e raised power tau d tau, you just get e raised power tau. So that is our uv minus integral of v. What is v now? V is still e raised power tau du. Du is when you differentiate, tau is equal to u. So d tau is equal to du. So this is just simply d tau. Okay. So, and of course, this is from 0 to t. That's all we have for that. So we can now say we have f convoluted with g in time is e raised power minus t. Then tau e raised power tau minus, when you integrate e raised power tau, the answer is simply e raised to power tau again. And now from 0 to t. Okay. Oh no, everything, yeah, everything is from 0 to tau. Okay. So yeah, so even this, right? Even this here should still be from 0 to t. Okay. Then now e raised power t from 0 to t still. Okay. So yeah, I guess we can move on from here. So we can now say we have f convoluted with g in time is equal to e raised power minus t, then into, okay, because this is also from 0 to t. So if you put the t at the top, we have t et. Then if you put 0, that would just be simply 0, because 0, uh, when when t is 0, so it means tau is 0, e raised power 0. So 0 could just cancel that out, minus. Here now we have when tau is t, we have e raised power t minus when tau is 0, so we have e raised power 0. Okay, that's what we have for that. So here these are like 0, e raised power 0. And of course the 0 just cancels everything out. So we can simplify this now. So this is e raised power t into TET minus 0 minus e raised power t, then minus 1, because e raised power 0 is 1. We open all of that up like that. So this is e raised power minus t, e raised power minus t into t e raised power t. 0 is gone, minus e t minus 1. So we can open this up, okay? E raised power minus t times t e t is simply t, because e raised power minus t will cancel this. Then when we come here, e raised power minus t times e raised power t is 1. Then e raised power minus t times minus 1, that's e raised power minus t. Now, does this look like what you've seen before? I believe so. This looks exactly like, well, when we did the first method, what we got, t minus 1 plus e raised power minus t. This is exactly this t minus 1. Is it minus now? It should be plus. Is it plus? I think it's minus. Oh, it's plus. It's plus, it's plus, it's plus. Okay, so let me see. Why is it plus? It shouldn't be plus, I believe. How did we do it? Let me see again. Okay, this is minus 1. I think it's plus. Yes, it should be plus really, because this is plus here. This is also plus. Yeah. No, here is minus t. This is plus 1. Then when we multiply this, this is plus. Yeah, this is plus. So that this can now be plus. Yes, this is it. So, and of course, this is similar to t e raised power t, because if you put 0, this is 0, this is 1, 1 minus 1 minus 1, that's 0. 0 times that is 0. So if you put 1, 1 minus 1 is gone. E raised power minus 1 is still the same e raised power minus that. If you put 1, right? If you put 1, oh, this is actually t e raised power minus t, sorry. Yeah, if you put 1, then it's exactly the same thing, just like what we did up there before now. So they are exactly the same. T e raised power minus t, right? Yeah, t e raised power minus t. So if you put 0, if you put 1, if you put any number, they are the same. So now with this, now we have gone back to the idea of inverse, and this is what we have. So that's just a revisit to that idea of inverse. So at this point, let's just take some practice questions as we round this off. So don't forget the deal is here is just about the transform, but I just revisited the idea of inverse transform just to remind us of that. Okay. So you want to practice the following. Find the Laplace transform. Find the Laplace transform of the convolution f convoluted with g in time for the following. Number one, you have f of t equals e raised to power 3t, and then you have g of t equals cos 2t. Okay, that's the first. Number two, f of t is t squared, and g of t is e raised to power minus t. Number three, f of t is sine t, and g of t is equal to cos t. Number four, f of t is e raised to power t, g of t is t raised to power 3. Number five, f of t is e raised to power minus 2t, g of t is t squared. Okay, g of t is t squared. Okay, so feel free. Of course, don't forget, start by finding the Laplace transforms of f and t individually. Then use the convolution theorem to multiply the Laplace transforms to find the Laplace transformation of the convolution. If needed, refer to standard Laplace transform like this of exponential, sine, cosine, and polynomial functions. That's how we've been doing all that. All right, so let me see your answers in the comments, either on YouTube or on Facebook. All right, let me also know how helpful these videos are for you. And feel free to, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And if you have not subscribed already, please feel free to subscribe. And for those who have subscribed, thank you so much. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.